Okay, so we're back for the fourth time. This time we'll be discussing the stats and probability paper that I took on Monday. So this one wasn't too bad actually. I did a lot of preparation for it. Just to take a look at this cheat sheet that I brought into the exam. So yeah, a lot of it I scribbled on because I realized there was quite a bit I was missing. But yeah, we've got some residual sum of squares on here, correlation stuff, Pearson's product one correlation coefficient, confidence intervals for the expected value of something, linear regression models, more confidence intervals, more confidence intervals, but this time for linear regression, hypothesis tests. Yeah, you got the variance hypothesis test, equality of variances, mean, difference of means, paired t-test, that kind of stuff, and residuals there. A variance formula. If we go over here, this is the probability side. We've got Bayes' theorem. These equations here for combining variances and expected values for independent variables, marginal probabilities, more expected values and stuff. Um, what else? Oh yeah, distributions and their uses. I remember while I was writing this, I actually thought it ended up being useless, but I wrote it just in case. Turns out it wasn't, but yeah, we'll get into that in a second. Approximations from binomial to Poisson and Poisson to normal. Covariance, correlation again. Going from CDF to PDF, then PDF to CDF. Of course, integrated intervention, that kind of stuff. And this is just for a difference of proportions hypothesis test. There's a value PC that I forgot what it was, had to write down. But yeah, that's the sheet, and let's look at the exam now. Alright, so there was 9 questions, of course 100 marks. The first 50 marks were based on probability, and the second 50 marks the second half were based on statistics. So let's take a look at this. Alright. A group of friends regularly eat out at their favorite restaurant on a Saturday evening. After their meal, they always decide jointly whether the quality of food was good or not good. The restaurant has 4 head chefs, A, B, C, and D, who work on Saturday evenings, 35%, 30%, 20%, and 15% of the time respectively. Quality of the food prepared by each chef is rated good by the friends with a probability of 0.4, 0.5, 0.8, and 0.9 respectively. Calculate the overall probability that the quality of the food is rated good. For this one, I remember I just multiplied each work rate with their, of course in decimal form, with their respective good probability. So I did 0.35 times 0.4 plus 0.3 times 0.5 plus 0.2 times 0.8 plus 0.9 times 0.15. I believe I got 0.585 for that one. A lot of my class seem to have gotten that as well, so I'm confident about this one. This one, I believe these two require Bayes' theorem. So yeah, because it's conditional, yeah, given that the food was rated good on their most recent visit, calculate the probability that the head chef B was on duty. So yeah, it's like yeah, given that the food was rated good, was Chef B working? I believe. Hold on. Honestly, I can't remember. I remember I did use Bayes' theorem. Yeah. Where is it? There. So remember, I said that the probability that the food was rated good, that this probability was equal to the probability that Chef B was working and the food was rated good times the probability that the food was rated good divided by the probability that Chef B was working. I did that. Um, that I got an answer for it that seemed kind of reasonable, but then again, um, I feel like a reasonable probability like answer is hard to really um, like uh, notice. So yeah, C wasn't too bad. I knew that since C had quite a high rate of having good food, his answer should be quite low, and it was. I got like 0.1776, so I think that's actually correct. Here, question 2. Yeah, suppose that you've been given the job of inspecting ceramic vases on a production line. The probability that any vase on the production line will be found to have a crack in it is 0.08. Okay, probability that the first vase you find to be cracked is the 8th one. This is actually where this came in. This is a geometric distribution where there's independent Bernoulli trials, and you're seeing how many it takes to get the first success. Of course, first one is correct. The first one's correct on the 8th attempt. Yeah, that wasn't too bad actually. I believe you end up just doing like the probability that the first that 7 are correct times probability that 1 is correct. So it'd be 1 minus 0.0808 to the 7 times 0.08, if that makes sense. I've got the thing right here actually. Yeah, geometric. So yeah, you just plug in 8 here and 0.08 for p, and yeah, you get your answer. That wasn't too bad. See, probability that the 10th vase you look at is the second one you found a crack in it. This is what I believe was a negative binomial. Again, I don't exactly know why it's called negative binomial, even though I think it's closer to a geometric distribution, but that's not important though. So yeah, it's basically where instead of finding just the first one, the first success, it's the rth success. So in this case, 2. So yeah, you just find negative binomial, plug in you just plug in r equals 2 here, and x equals 10 here. You get 9 choose 1 times 0.08 to the 2 times 1 minus p to the 0.0 to the 8. I mean, yeah, that's that question. That wasn't too bad. On this page here, the only one I'm a bit wary of was B, to be honest. The rest were fine. Next page. Random variable x has a probability density f of x equals where c is a finite positive constant. Find the expected value and show that the variance of x is equal to that. This was quite fine, honestly. Yeah, you just had to multiply this by x and then integrate it from bounds 0 and 1, and then that will get you c over c plus 1, I believe. And then yeah, for the variance one, you end up getting you have to find e of x squared. Like you have to do that basically. So yeah, times it by x squared, integrate it with the bounds and everything, and then you'll get, then you do that minus the square of that, and that gives you, of course, that gives you 2 different fractions, and then putting that into one fraction did give you that, so I'm confident about those 8 marks there. What standard distribution does x follow when c equals 1? This one I'm a bit confused by, because of course putting c equals 1 here, you just get 1, like, because the power of x becomes 0, anything to the 0 is just 1. So I end up just saying that f of x between 0 and, when x is between 0 and 1, f of x equals 1, otherwise it equals 0. If I lost that mark, I wouldn't be too surprised because I didn't really get the question, but oh well. Ooh, part C. When c equals 3, find the cumulative distribution of x and use it to show that the median is 0.7937, correct to 4 decimal places. Now, I'm so glad they gave us what the answer should be in this question, because if it was just find the median when c equals 3, I would have not understood what to do at all. But yeah, the first thing you had to do, I believe, was integrate this. Wait, no. Was it integrate? Yeah, integrate this, and yeah, you end up getting what's that? Oh yes, when c equals 3, so that then becomes 3x squared, 3x squared. Integrating that, you get x cubed, and then you set that equal to 0.5, and then cube root it. That gives you 0.7937. Good stuff, good stuff. Question 4. An ecology student is studying a population of 9 foxes and believes that the diameter of hairs from the foxes has a normal distribution with mean 32 micrometers and standard deviation of 8 micrometers. Using this distribution, calculate the probability of a hair having diameter less than 26 micrometers. This was fine, honestly. You just had to standardize this. So, using the x minus mu all over sigma. So, yeah, you would do 26 minus 32 all over 8. And then you would use this stats table here. You'd use this stats table here to find it. I believe you end up getting like minus a half in the end. Yeah, I believe so. Wait, no, was it minus 3/4? I think it was minus 3/4, yeah. What was Yeah, because 26 minus 32 is minus 6, and over 8, that's minus 3/4. So minus 0.75. Probability that z is less than minus 0.75 is, where is it there? 0.226. Not a bad question. 4b was much of the same, but this time it's more of a range instead of just, of course A was still a range, but you have two numbers to consider. So between 35 and 45 micrometers. This one you do probability that x is less than 45 minus the probability that x is less than 35. Of course, to do those, you have to standardize both of these. And I ended up having to do linear interpolation twice because those values don't appear in just this table. So yeah, but yeah, that wasn't too bad, honestly. This one, yeah, suppose like the random variables x and y have a joint probability mass function. Show that x and y are independent. My desk is a mess right now. Oh man. But show that x and y are independent. This one, I was able to do it, but I did it in a very long way. So I knew that two things are independent if the intersect is equal to just like the product. And I didn't know, and that was the only way I could think of actually proving that. So I literally took the marginal probability of x equals 1, then times it by the marginal probability that y equals 2, for example. Probability that x equals 1 is 0.1 plus 0.2 plus 0.1, that's 0.4. Probability that y equals 2 is 0.1 plus 0.15, that's 0.25. 0.4 times 0.25 equals 0.1, which is the probability that x equals 1 and y equals 2. I did that across all of these. Took about an entire page. I didn't know how else to do it, honestly, so yeah, that's that. I felt like that was a bit much for 6 marks, but didn't know how else I could really do that. Calculate the expected value of x, y. This one you had to take each pair of x and y, multiply them, get the product of those, and multiply them by the probability, and sum that across all cells. For example, you would just do 1 times 2 times 0.1 times 3 times 2 times 0.15. Oh wait, no, let me restart. 1 times 2 times 0.1 plus 3 times 2 times 0.15 plus 1 times 4 times 0.2 plus 3 times 4 times 0.3. Yeah, that. And then I ended up getting 8.8. So I did 2 others. I think there were some other answers in there, but I can't remember what other people said. 6. Yeah, this is just a simple question here. Diameter in microns of 25 cells from a culture of bacteria have been measured, resulting in a sample mean of 7.88, standard deviation of 1.14. Calculate confidence interval for the interval of the true mean diameter. That one was really fine, to be honest. Just using where is it? Yeah, here. Yeah, because we don't have the population variance, only the sample. We have to use the t-distribution to estimate it. So yeah, with n minus 1 degrees of freedoms, so 24 degrees of freedom in this case. And this one was just a hypothesis test. Yeah, seeing investigate whether the mean blood glucose level of the first students differs from the mean of the population, which is 4.9. That's just a regular t-test. Just using oh man, where is it? There, choosing that one wasn't too bad. I think I got it to be not significant, so we can't reject the null hypothesis of it being equal to that. So yeah, in a study, a scientist has measured the organic carbon content in sediments of 13 river sites, 13 pond sites. Here's the statistics. F-test for quality of variances. Yeah, not too bad. You just use this test statistic here compared to the F distribution. Or just making note that you make the bigger standard deviation S1, so then you're leaning more to the right of the distribution. So yeah, just had to keep in mind of that. That's whether the true mean organic carbon content is the same for the rivers and ponds. So yeah, I remember my lecturer said actually that for this kind of question, perform an F-test for quality of variances. If the next part does say to test to test if two different means are the same, then this is always going to come out as significant, no, as not significant enough to reject equality of variances, because you need equality of variances to use to do a two sample t-test, which would be this question here. So yeah, I knew that when I got that to be not significant, I was on the right track. Last page here. I'm at a university, a sample of 120 undergraduates and 85 postgraduates. Part-time jobs were asked whether they regularly worked more than 10 hours per week. In the sample, 65 of the undergrads said yes, 62 of the postgrads said yes. So yeah, this was a difference in proportions test. So yeah, just using this one here. This is where PC came in. Yeah, of course, that's what number of individuals in both samples with the characteristic over the total sample size. So that's where that came in. Yeah, that question wasn't too bad. Calculate a 95% confidence interval for the difference in the two population proportions. Also, that was alright as well. Just using this one instead, really. Nothing too bad. Then table below gives the average food consumptions in pounds over a 350-day period from 50 egg-laying hens of each of 10 strains of a white leghorn. Average body weight of from the 50 hens in pounds also given. Now, for this question, I remember thinking, so that on the x-axis, it's the average body weights, right? So therefore, if x equals 0, that means the average body weight is 0. So there are no hens for that specific observation. So I thought to myself, surely that must mean that if there's no hens, that means no food can be consumed. So I ended up using a formula that forced the linear regression model through the origin. So like there's no y-intercept. Well, it is, but it's just it's 0. Where is this? I'll write it down. Where is it? Oh yeah, here. So it's the sum of xy over the sum of x squared. So I did 4671.1 over 249.54. I did that. From what I know, I'm the only person that did that, but didn't ask a whole lot of people. Everyone else just did a regular regression model. That could be wrong, but honestly, I guess we'll find out when the results come out. Interpret your parameter estimates. So yeah, I just said that. I can't remember what I got from. I think I got 18.711 maybe. Can't remember. It was 2 days ago now, but I said that for each pound increase in the average body weight of the 50 hens, the average they consumed on average 18.711 more pounds of food. This one was alright, to be honest. Just had to calculate. Where is it? Where is this? Over here. Yeah. I just had to calculate SXY and SXX. Wait, that's not it. Oh yeah. Had to calculate SXX and SXY. So some of the products and some of the squares for x, and then square this to get that. And yeah, I believe it came out to be 66.99. So that means that it came out to be 0.6699, and that means 66.99% of the variation in y is explained by x. So yeah, that's the end of the paper, as you can see. I'd say that was probably one of the better papers, actually. I'd say so far the one that went the best is I want to say between this or linear algebra, to be honest, because of just how much I prepared for linear algebra. But I haven't had any bad papers so far, honestly. But yeah, I'd say this is also one of the almost less interesting papers to look at. You know, it was just the questions weren't too difficult. So yeah, but yeah, that's the end of that. My next paper is on the 31st in 2 weeks' time. It is real analysis, so that is going to be interesting to say the least. But yeah, I do have a couple video ideas I'll probably film in between then, so you guys won't have nothing for 2 straight weeks. But till next time, have a good one.